continuing with coordinate proofs, we're going to start talking about coordinate proofs of quadrilaterals. We really did kind of do this before when we talked about coordinate proofs with parallel lines and perpendicular lines. It's really going to be some of the same process there. There are certain things we're going to have to remember about quadrilaterals in order for this proof to work. So the first thing we're going to do, example 1 says we're given this figure here. So first of all, we're going to have to graph it. And we're supposed to prove that it is in fact a parallelogram. And if you remember from the definition of a parallelogram has two sets of opposite sides parallel, which means when we graph this, we're probably going to have to find the slope. So starting off, let's graph this. We've got 3, 2. So 3, 2 is A. And then we have 8, 2. B, 5, 0 is C, 0, 0 is D. So I'm going to go ahead and take my straight edge and connect this. Let me find my straight edge. There it is. And connect these. It does look like a parallelogram, but remember we can't just say it's a parallelogram based on our assumptions there. We're going to have to actually prove it. Right, since we are proving it is a parallelogram, I'm going to go ahead and find the slopes of the opposite sides to see if they are congruent, and then the slopes are the same. And then we can actually write down what we know and what we have. So if we look at AD, the slope, I'm going to go rise 2 and run 1, 2, 3. So the slope is 2/3. Okay, if we look at the other side, the opposite of DA, we've got CB, so I'm going to also rise 2, run 3. That means that those two are parallel. I'm going to kind of slide over and write that down. Remember, we're finding the slopes. So the slope of AD is 2/3, and the slope of BC is 2/3, which means that AD is parallel to BC. So that's going to help us out first of all. Next, let's look at the other sides here. AB has a slope of 0. DC has a slope of 0 as well. So, again, we were looking at slopes. The slope of AB is 0. The slope of DC is 0. Therefore, AB is parallel to DC. Since we have both sides with both pairs of opposite sides parallel, we know that we do in fact have a parallelogram based on the definition of a parallelogram. So we have finished example 1. We have proven that this is in fact a parallelogram using slope of the figure. So that's how we prove something is a parallelogram. Let's look at what example 2 says. So example 2. In example 2, we are again given a figure. It is actually the exact same figure, but we're going to graph it again. And it says, prove that the diagonals of ABCD bisect each other. Now, if you remember, bisect means it's cut in half, or also that the pieces where the intersection point is, that those would be the same distance. So we're going to go ahead and graph this again so that we have the same figure. We have 3, 2 for A. B is 8, 2. C is 5, 0. D is 0, 0. Okay. However, we do need to add to this parallelogram. The diagonals should bisect each other, by the way, because that is one of the properties of a parallelogram. But let's just check to make sure, obviously, since that's what we're proving. All right, but before we can do this, we actually need the diagonals. So let's draw our diagonals in. So here's what we are looking for. I'm going to go ahead and label this point E as well. And E is at 1, 2, 3, 4, 1. So E, I'm going to write it up here. Is at 4, 1. And we're going to use those to determine if the diagonals really bisect each other. If the diagonals bisect each other, that means DE would be congruent to BE, and AE would be congruent to CE. So that's what we're actually going to find. So I'm going to move this over. You've got these points. I'm going to use those with the distance formula to actually see if these diagonals bisect each other. So as I stated, we need to find the distance of AE and the distance of CE. Looking for a measure there, not naming the segment. So to do that, I'm going to use the distance formula. This is one you should have memorized by now. A is 3 minus E of 2. And again, 2 minus 1. I will determine that in a moment. Let's go ahead and set up CE. C5 minus 4 squared plus 0 minus 1 squared. And we're going to go ahead and keep this as a in a square, in radical form. 3 minus 1 is negative 1. Negative 1 squared is 1, plus 2 minus 1 is 1, and that squared is 1. So AE is the square root of 2. CE, 5 minus 4 is 1, and 1 squared is 1. 0 minus 1 is negative 1. Negative 1 squared is 1. So CE is also square root of 2. Which means AE is in fact congruent to CE. This also means that E bisects AC. So that helps us. Now let's look at the other two, because it only bisects each other if the other two are also congruent. So BE and DE. BE, we have 8 minus 4 squared plus 2 minus 1 squared. Okay, if we want to simplify that, 8 minus 4 is 4. 4 squared is 16. Plus 2 minus 1 is 1, and 1 squared is 1. So BE squared is 17, and we're hoping that DE is the same. So using the points, D is 0, 0, so 0 minus E of 4 squared plus 0 minus 1 squared. 0 minus 4 is negative 4. Negative 4 squared is 16. That's promising. 0 minus 1 is negative 1. Negative 1 squared is 1. So square root of 17. So they are, in fact, congruent, which is what we needed. Good. Since these are congruent, so since... It's not working. Since AE is congruent to CE and BE is congruent to DE, then we know the diagonals do bisect each other. That one was a little longer. It depends on what you're proving, exactly what, how long your proof is going to be. We're going to talk about 2 more examples to finish this lesson. Okay, so if you were watching this, this would be the second day. We would only probably get to 2 examples in the first day to allow some time to work on these. So example 3 and 4 both would be in a second day here. We're still proving certain things about quadrilaterals with coordinates. So we're going to go ahead and graph example 3. Let's see what it actually asks for, though. So example 3, we're given this quadrilateral that we're going to graph in just a moment. And it says use diagonals to determine whether a parallelogram with the given vertices is a rectangle, a rhombus, or a square. I believe example 4, we're going to look, actually has the exact same directions. So we need to remember some things about diagonals in just a minute after we graph them in order to prove this. And I'm actually going to write that over here. Here's what we need to have memorized about diagonals. We already know it is a parallelogram. Parallelogram, each of them, the special types of parallelograms, have certain rules. For instance, a rectangle, the diagonals of a rectangle are congruent, meaning they have the same distance for coordinate purposes. For a rhombus, they are perpendicular, which just means that we could find the slopes of them and show that they have a product of one or what we're used to, opposite reciprocal. And a square has both congruent diagonals and perpendicular diagonals. This is going to help us determine whether the parallelogram is a rectangle, rhombus, or square. So we're going to go ahead and graph these. I've got -5, -1, -1. That might help if I graphed it correctly. -2, 4. 3, 1. And 0, -4. I'm going to graph it. Remember, I'm looking at diagonals, which means in just a second I'm also going to have to draw the diagonals. Sometimes you can look at it and see what you think it might be. This actually looks like it's probably a square, which means I'm probably going to have to try both the distance formula to see if the diagonals are congruent and find the slope to see if they're actually perpendicular. But let's go ahead and draw in the diagonals. I do already know they bisect each other because it says it's a parallelogram, but that doesn't necessarily help me for these purposes. Okay, so I'm looking at the diagonals. So I'm actually trying to determine if, first of all, if we want to show if it's a rectangle or not, we're trying to determine if LN is actually going to be congruent to KM or MK. So let's look at that first. Using our distance formula, L to N, so -2 minus 0 squared, plus 4 minus -4, or plus 4 squared. This is a -2, and that squared is 4. This is 8, and that squared is 64. So I have the square root of 68. I'm not going to reduce that. I could, but for our purposes, reducing it is irrelevant. We would only have to reduce if this didn't come out to square root of 68 to see if it actually was the same. But we'll see. Alright, so K, -5 minus 3 squared, plus -1 minus 1 squared. -5 minus 3, add, keep the sign. We have a -8, and -8 squared is 64. Plus -1 minus 1 is -2, and that squared is 4. So we did get square root of 68. Which means LN is congruent to KM. Which means this is a rectangle, but we need to keep going to see if it is also a square. So to determine if it is also a square, we will need to find the slopes. So find the slope of Ln and Km. Ln is negative 8 over 2, which reduces to negative 4. Km is 2 over 8, which reduces to 1/4. We've talked about this before with perpendicular. These are opposite reciprocals, or their products is negative 1. Therefore, they are perpendicular. So Ln is perpendicular to Km because their slopes are either opposite reciprocal, or if you multiply them together, their products would be negative 1. So since Ln is congruent to Km and Ln is perpendicular to Km, we know that KLMN is a square. So that helps us out. We've got both properties of the diagonals are true. Example 4 is the exact same directions. So I'm going to leave it there for a second. It'd probably be a good idea if you tried it yourself. I'll show you the graph here. You're supposed to determine whether it is a rectangle, rhombus, or square. It's always a good idea to practice on your own. If you were doing this and not just watching it for review. Okay. So I'm going to go ahead and graph. I can go ahead and see this does not look like a square because it's kind of slanted, which means it doesn't probably have a right angle. Since it probably doesn't have a right angle, I'm pretty sure it's probably not a rectangle either. And I'm just going to go ahead and assume that. I mean, looking at this is not a rectangle, not a square, so there really isn't any point in trying it. That means the only thing that's left is rhombus, so we need to hope that the slopes are opposite reciprocals or their product are negative 1. So that's what we're actually going to find is the slope. So we're going to find the slope of the diagonals, the slope of PR, and then the slope of QS or SQ. I'm going to write that down so we remember that's what we're finding. We're finding slope, the slope of PR, and in a minute the slope of SQ or QS. Okay, PR. I'm going to go down 7. And over 1, 2, 3, 4, 5, 6, 7. Which reduces to negative 1. Okay. Then SQ. I'm going to go up 5. And over 1, 2, 3, 4, 5. So 1. This is where having the products helps. Remember, you do have to reduce because these do not look like they are opposite reciprocals at this point, or that they would multiply to give you a negative 1. But this is where the multiplying by negative 1 really helps you out. Neither of these are a fraction, but 1 times negative 1 is negative 1. So that's what I'm actually going to write as our instructions here. The diagonals are perpendicular. I'm going to write that right here. PR is perpendicular to SQ. So the diagonals are perpendicular. Because their slopes have a product of negative 1. Therefore, PQRS is a rhombus.